All right, today we are starting chapter 4, the infamous chapter 4. Now, to be completely honest, the first couple of sections in chapter 4 are really incredibly easy. Okay, it's the last couple of sections that really will challenge you. Okay, many people that I've taught stat to over the years have mentioned to me that they thought chapter 4 was the absolute worst part of the whole course. It's not the whole chapter. It's just the last couple of sections are pretty challenging. So I've got some interesting misleading statistics today. This happened during World War I. Helmets were almost withdrawn from British soldiers. What about that? When Britain started issuing steel helmets to all soldiers, generals began to call for their removal. Why in the world? Someone gets hit in the head by some shrapnel and lives, the person is a casualty. If they die from a bullet, they are a fatality, and they don't appear in the casualty statistics. From a statistical standpoint, adopting helmets drastically increased the number of casualties. The helmets increased the number of casualties because head wounds were no longer fatal, they lived, okay? So the casualty rates went up. Fatalities dropped dramatically, but the number of injuries went up because the steel helmet was saving the lives. The soldiers were still injured, okay? And the generals just looked at the casualty reports and saw that the casualties are up from wearing helmets. And they thought, this is ridiculous, let's not wear helmets. Oh no, you gotta get the whole story. The same thing happens today with cyclists. If you ride a bicycle or a motorcycle, wearing a helmet, okay? Number of cyclists being treated for head wounds has increased. That's because previously, they wouldn't have even been treated. They would have been dead. Okay, good friend of mine. He's a real bicycle fanatic. He was in an accident. His helmet was literally cracked in 2 pieces. And he had a massive headache for a couple of days, but he was fine. Absolutely fine. Situations like the cyclist that I just talked about can also be attributed to something called the Peltzman effect, which is also known as risk compensation. The effect of a person being aware of greater safety. I don't have to worry about anything because I have a helmet on. I can now do all kinds of crazy, weird stuff, like ride my mountain bike down over a mountain at 60 miles an hour, you know? So there's 2 reasons why there can be an increase in injuries. Peltzman effect, doing crazy stuff because you're wearing a helmet, or the injuries have increased because the fatalities have decreased. Very interesting. Now, there was a statistician named Simpson. We're going to talk about Simpson later on in this course, but here is just one illustration of this, very similar to the whole helmet thing. Suppose hospitals 1 and 2 are nearby. One is better equipped for serious injuries. So proportionally more of the people taken there are really badly hurt. Hospital 1 does better than hospital 2, okay? Since people who are badly hurt are more likely to die than people who are not badly hurt, whether or not they go to 1 or 2, hospital 1 may still have an overall higher death rate, even if it's a better hospital, because the worst cases go there, okay? So just because hospital 1 has a higher death rate, you can't necessarily be certain that there are a bunch of crummy doctors. Super Freakonomics is a fantastic book. I highly recommend you reading that book. It's just an amazing book. The same thing happens with doctors. Good doctors are generally given the tougher cases, while bad doctors may have the easier cases. So if you're looking at death rates, you may see some doctors have higher death rates, but that usually happens with really good doctors because they get the really tougher cases, and unfortunately, oftentimes their patients die. On our first day of class, we talked about some different biases. I wonder if you remember any of the biases, like, for instance, if you let people self-select whether they're going to be a part of a study or not, like we talked about abortion, guns rights, those kinds of things, people get real fired up and they're biased and they want to be a part of that study, and you're going to get biased results. You're going to get a lot of people saying yes, a lot of people saying no, okay? There's other bias. This is called a bias of scrutiny. Oh, I should mention also, remember, if you select from a specific population, like if you do a survey at a gym, right? If you do a survey at a gym, you're probably getting healthier people taking your survey because you're selecting from a specific population. This is something that a professor in England worked on, Melissa Bateson. She called it a bias of scrutiny. Are you being watched? Okay. She had a coffee urn in the faculty room. Every week she posted a new price list. The prices never changed, but a small photograph at the top of the sign did change. On odd weeks, there were photos of flowers at the top of the price list, and on even weeks, there were a pair of human eyes. Well, you know what happened. Almost 3 times as much money was collected during the even weeks when there were eyes. It appeared as though someone was watching and people responded differently. The bias of scrutiny. Are you being watched? Okay, so chapter 4. Main topic in chapter 4 is probability. We're going to get away from z-scores. We're going to get away from standard deviations, from box plots. Okay, talk about probability. 3 coins are tossed. What's the probability of getting 2 heads and a tail? Now, I've seen people do it in this way. When you toss 3 coins, you can get all heads. You can get 2 heads and a tail. You can get 1 head and 2 tails, or you could get all tails. So there's only 4 possibilities. So what's the probability of getting 2 heads and a tail? 1 out of 4. Because probability, what is probability? Okay? If an experiment can result in n different outcomes, the probability of one of those outcomes occurring would be Q over n, where Q is the number of ways that outcome could occur. In other words, this is a fancy way of saying is, what's the total sample? What it could actually happen in an experiment, okay? What do I want to happen goes on top of the total goes on the bottom, all right? So let's go back up to these 3 coins. When you toss 3 coins, what could you actually get? You could get head, head, head. You could get head, head, tail. Head, tail, head. Tail, head, head, right? You could get tail, tail, head. Tail, head, tail. Head, tail, tail. Or you could get tail, tail, tail. Those are the only ways that 3 coins can come up. Now, what is your total sample space? There's 8 different ways things can come up, the coins. You want 2 heads and a tail, and there are 3 of them. Probability, 2 heads and a tail is 3 out of 8, not 1 out of 4, okay, that I had mentioned earlier. How about a survey was done of SU students' opinion of intro to STAT, right? Rating from 1 to 10. And if I said, what's the probability of selecting a student who loves STAT? Well, they would have the higher rating. Okay, so what is the total sample space? Like here it was 8. What's the total sample space? I've got to add up all those different responses. I get a total of 2,100 students were surveyed. What's the probability? I want to take 1095. What I want, 1095 divided by 2,100, and I get better than 50%. Yeah, more than half of the students surveyed love STAT. I agree. Okay. Two die are rolled. What is the total number of possible outcomes? If the first die comes up a 1, the second die could come up 1 through 6. If the first die comes up a 2, the second die could be 1 through 6. If the first die came up 3, the second die could be 1 through 6. For each of the first die's side, and there's 6 sides, right? 6 sides. That second die can come up 6 different ways. So you have 6 times 6, there's 36 different outcomes. What's the probability of getting a sum of 8? I know there's 36 different outcomes. How can I get an 8? I could have a 2 and a 6, a 6 and a 2, right? Because they're different die. 2 and a 6, 6 and a 2, a 3 and a 5, a 5 and a 3, or a 4 and a 4. I could have 5 chances out of 36. Make that a decimal. It's preferable if you make them all decimals. That's 14% chance, or 0.14. What's the probability of getting a double? 36 total. You could have a 1 and a 1, a 2 and a 2, a 3 and a 3. So there's 6. 6 out of 36 divided out will be 17%. Which sum is most likely? Which sum is most likely? Try 7. If you want to get a 7, there's still 36, right? But to get a 7, you could have a 6 and a 1, a 1 and a 6, a 2 and a 5, a 5 and a 2, a 3 and a 4, a 4 and a 3, which is 6 out of 36, or 17%. And there is no other sum that comes close to that. Closest one would be this one, okay? Getting an 8. But it's getting a 7. When you roll 2 die, the most popular sum is getting a 7. All right, some basic facts of probability. Check over those. Probability is always between 0 and 1, including the 0 and 1. 0 is when it's impossible. 1 is when it's certain. Okay? Like, for instance, if you roll 2 die, the probability of getting a sum between 2 and 12, inclusive, 2 and 12, including the 2 and the 12, is 100% chance, right? Or 1. Now, a frequentist assumes there will be a large number of trials, okay? I'm not really big into the frequentist idea. You got a couple problems on your homework with it, but there is one thing that's interesting. We know when we flip a coin, the chance of getting ahead is 50-50, 50% or half. It's assumed that that answer comes from doing many, many flips. That's a frequentist assumption, many flips. Suppose you flip a coin 10 times, you get 8 heads. That's possible. Flip a coin 10 times and get 8 heads. Would you bet $1,000 that your next flip would be a head? I wouldn't. With just 10 flips, right? But what if you flipped a coin 1,000 times and you got 800 heads? Whoa, something weird's going on there, because it should be very, very close to 500. Check out the graphs on page 148, where they have computer simulations of coin tosses, and everything kind of fluctuates early on in the beginning, but after a while it evens out to right around 50-50, 50% chance, okay? So you're gonna have a couple problems in the homework where it talks about frequentists, but that just assumes you have lots and lots of trials. This is really, really interesting, and I hope you can get something from this. A study of the incidence of kidney cancer in the 3,141 counties of the United States revealed the probability of someone getting kidney cancer is lowest in counties that are mostly rural, sparsely populated, and in red states, Republican states. What is that? So the probability is lowest of getting kidney cancer in those kinds of situations. Wow. A benefit of being a Republican. How about that? Consider the counties where the incidence of kidney cancer is the highest. You're most likely to get kidney cancer if you live in a rural, sparsely populated Republican state. What the heck is going on? How can you have the lowest and the highest rates in rural areas, sparsely populated? How is that possible? And here it is. Extreme outcomes are more likely to be found in small samples than large ones. You've all heard studies done where people say there was pollution in my water, my neighbor got cancer, a little kid down the road got cancer. We're all getting cancer, okay, from the pollution in the water. You've got to temper that. Extreme outcomes are more likely to be found in small samples than in large ones. And here's a good illustration of that. Suppose a jar is filled with marbles, half of them are red, half of them are white. Jack and Jill are going to play a game, okay? If Jack gets 4 marbles that are all red, okay, and then he puts them back in, all right, he gets a point. If he gets 4 red, he's going to pick out 4 marbles, hoping to get 4 red. If Jill draws 7 marbles, hoping for all white, if she gets 7 white ones, she'll get a point. Who's going to get to 10 first? Well, it's obvious. Jack is going to get to 10 first. Small samples, 4 marbles, picking 4. He's more likely to get all red than Jill is to get all 7 white, right? Perfect example of small samples yielding extreme outcomes more readily. Okay, we're going to be doing a lot of problems with cards. You need to know a standard deck of cards has 52 cards. There's 13 of each suit. There's 4 suits: clubs, spades, hearts, and diamonds. Everybody understands that clubs and spades are colored black, hearts and diamonds are colored red. Okay? Everybody with me on cards here? This is a standard suit. 13 cards per each one of these. 13 times 4 is 52. Here's the 13. You have numbers 2, 3, 4, 5, 6, 7, 8, 9, and 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9 of these. Then you have 4 of these cards, makes a total of 13. The jack, the queen, and the king have faces on them of a jack, a queen, and a king. These are called face cards. The ace is not a face card. Okay? So you need to know that to be able to do probability problems. What's the probability of getting a red? Okay? The hearts and diamonds are red. The clubs and spades are black. 50-50, 50% chance of getting a red. What's the chance of getting an 8? There's a total of 52 cards. What do I want to do? I want to get an 8. How many 8s are there? There's 1 in clubs, 1 in spades, 1 in hearts, 1 in diamonds. 4 out of 52, change it to a decimal. 4 divided by 52 is right around 8% chance, okay, of getting an 8. The probability of not getting a spade. If you don't want spades, you can have one of the other 3 suits. There's 3 suits you could accept out of 4. Which is 75%, correct? Another way you could have done this, not getting a spade, would be a club 13, a heart 13, a diamond 13. That's 39 out of 52. And 39 out of 52 will still give you 75%. Probability of getting a face card. There are 3 face cards in every suit. 3 times the 4 suit, there's a total of 12 face cards out of 52 cards. 12 divided by 52, and I get 23%. Okay? What's the probability of getting a black ace? There's an ace here and an ace there. It's 2 out of 52. 2 divided by 52 is right around 4% chance of getting a black ace. The probability of not getting a number. Not getting a number. So you only have 1, 2, 3, 4 non-numbers in each suit. So there are 16 cards that are not numbers in the whole deck out of 52. 16 divided by 52 is right around 31% chance. Okay? Pretty easy stuff. Now, obviously, if you're reading this and you are not in class, or if it's an online course, you'd use that information for your homework today. And here is the homework. If we're in class, we're going to be determining these problems by the people in our class. For everybody else, you have to go back to the previous screen to use that information. When you get up to the right and left-hand problems in that section, okay? Actually should be an extremely easy assignment.